So let's start by looking at some example problems of kind of the last thing that we talked about on Friday. I had made mention of the fact that we can use osmotic pressure to determine the molar mass of a substance. And if you look at the lab that you're doing tomorrow, that's exactly what you're going to be asked to do in that lab tomorrow, is not osmotic pressure. You'll actually be doing a different calculation. You'll be doing freezing point, but the idea is basically the same. In the lab tomorrow, you'll work backwards to figure out molality and use the molality to figure out moles and molar mass. Here we're using osmotic pressure to do the same thing. So let's take a look at an example problem of how to do that to give us a little bit better preparation for that when it comes. So we're told we have a 47 milligram sample of a water-soluble non-electrolyte isolated from a South African tree. Sample was dissolved in water to make 2.5 milliliters of solution. The osmotic pressure of the solution is 4.89 atmospheres at 25 Celsius. What we want to know is what is the molar mass of the compound. So there's a lot of information in here, but remember that we're talking about osmotic pressure. Calculation for osmotic pressure is I times the molarity of the solution times the gas constant R times the Kelvin temperature. Well, we've got some of this information here already. We've got an osmotic pressure, so there's our pi. We've got a temperature. We just need to convert it into Kelvin. There's our T. R is a gas constant. We can pull that off of a table of values. The only thing that we're missing is we're missing the molarity and we're missing the value of I. But we do have a clue about the value of I. The fact that this is a non-electrolyte means that it does not break apart in water. If it doesn't break apart in water, then it isn't an ionic compound. And non-ionic compounds have a Van Hoff factor I of 1. So if I start putting this all together now, I've got most of the information that I need. I've got a pressure. I've got the Van Hoff factor of 1. I don't know what the molarity is yet, but that's probably what I need to find. Since my pressure unit is in atmospheres, I'm going to use the value of R that is also in atmospheres. And temperature, 25 Celsius plus 273, is going to give me 298 Kelvin. So when all is said and done here, I've got everything I need but the molarity of the solution. And if I move this over just slightly, I would have 0.489 atmospheres divided by 1 divided by 0.0821 liter atmospheres over moles Kelvin and 298 Kelvin. Now, if I do the calculation here on the left, atmospheres cancel, Kelvin cancel, I'm left with 1 over liters over moles. So I've got the reciprocal of the fraction liters over moles. Reciprocal of a fraction just flips that fraction over. So 0.489 divided by 0.0821 divided by 298. I get the three significant figures, 0.0200 moles over liters. So that's the molarity of the solution. That's not what we've been asked for, though. What we need is the molar mass. For molar mass, I need grams of the sample divided by moles of the sample. Well, I've got the grams already. 47 milligrams is 0.047 grams. For the moles, I've got a molarity. Do I have any other information here that might be useful? Yeah. We haven't used this 2.5 milliliters of solution yet. Now, where it becomes useful, if I convert it to liters, molarity times volume in liters will give me moles. 0.02 times 0.00250 is going to give us 5.00 times 10 to the negative fifth moles. So if I put that value in here at the bottom, 5.00 times 10 to the negative fifth moles. To two significant figures, because we only have two in the numerator, I get a molar mass of 940 grams per mole. So that's what I'm looking at for this problem, 940 grams per mole. Where we see this most often, if we're talking about like real applications, not just book problems, we see this kind of application used often to help characterize biological samples. Like this one. We got this compound from a tree. We don't know what its molar mass is, but we also know we don't got very much of it. We can find its molar mass this way. And what will happen often is that we will get compounds that are very, very large in their molar mass as a result. Because biological compounds tend to be very big in their molar masses, tend to be very big in their structures, because they tend to be more polymer-like. All right, any questions with this example before I let you try one here on your own? Okay, very similar kind of problem. You have an aqueous solution made by dissolving 11.9 milligrams of a non-electrolytic protein in enough water to make 4.88 milliliters of solution. if the osmotic pressure is 523 millimeters of mercury at 25 Celsius, what is the molar mass of the protein? And I've given you the value of R for millimeters of mercury so that you don't have to look it up. So take a few minutes, walk back through the process that we just went through, and see if you can come up with a reasonable answer to this question. In about 5 minutes time or so, we'll go through the problem. We'll see how everybody did. All right, let's see how we did. So, kind of walking through the process here. Again, it's very similar to what the last problem was. So, we've got our I value at 1 because it's a non-electrolyte. This time it is 523 millimeters of mercury as our osmotic pressure. Temperature is still 25 Celsius, 298 K. So if we plug them into our osmotic pressure calculation here, we should get a concentration of 0.0281 molar. We need to multiply that concentration by the volume, 4.88 milliliters, would be 0.00488 liters. That's going to give us a number of moles, 1.37 times 10 to the negative fourth. And so the last step would be to take our mass, our mass, 11.9 milligrams, which is 0.0119 grams, and divide it by our number of moles, 1.37 times 10 to the negative fourth. And that would give us our molar mass here of 86.8 grams per mole. Now, I just got done saying biological samples usually have large molar masses. And yes, they usually do. This one, and for a protein, this mass is unusually small, which would lead us to one of two conclusions. Either it's not actually a protein, or somewhere we made a mistake in the experimental procedure in terms of how we measured everything. And so our best course of action there would be to go back and try to replicate the results. All right, any questions with this example? Kind of the last example we're looking at before we do anything related to vapor pressure. All right, then we will move on. So we've explored this concept before, the idea of osmotic pressure, the idea of vapor pressure. When we have a liquid substance, it evaporates. And if we collect that evaporated liquid, we will be able to measure how much it evaporates by how much pressure it exerts on the surroundings. Now in chapter 6, we related this idea to the concept overall of intermolecular forces. The more something evaporated, the higher its vapor pressure was, the worse its intermolecular forces had to have been. Because if you have strong intermolecular forces, you're not going to evaporate, you're going to stay in the liquid phase. Now, we made a direct relationship between that idea of temperature and surface area and intermolecular forces in chapter 6. There's one other factor that can play into how and vapor pressure is ultimately going to be shown. And that is, well, what if it isn't a pure substance? Now, if it's a pure substance, then all we have to look on is those three factors that we talked about in chapter 6: temperature, surface area, intermolecular force. But if I have a mixture, we know that the intermolecular forces don't only exist just between a substance and itself. If it's in a mixture, it's going to exist between the substance and the other substances in that mixture. And so the strength of adding those forces should have an impact on the vapor pressure itself. And it does. Since making these mixtures is going to increase the amount of intermolecular force inside of that solution, we're going to see a lowering of the vapor pressure. Because those intermolecular forces are going to be stronger, which means less evaporation and less gas molecule present above the solution to cause that pressure to take place in the first place. Now we can measure this using something called Raoult's law. Raoult's law, and this is where we use mole fraction, by the way. Raoult's law tells us that the vapor pressure of a solution is related to two factors: the concentration of the solvent and the vapor pressure of that solvent. So the big takeaway, the thing to notice here, is that we are going to have to calculate the concentration of the solvent in terms of its mole fraction in order to figure out how the vapor pressure is going to change. The other part of this equation, the vapor pressure of the solvent, this is not something that you are going to have to calculate. This is something that is going to be given to you as a table of values. So if you've looked in the laboratory, you see we have all of those reference books. This is the kind of material that's in those reference books. What is the vapor pressure of water at 25 degrees Celsius? I can look it up in the CRC handbook, find it. That's the value I would use in this particular circumstance. What is the vapor pressure of benzene at 15 degrees Celsius? Again, table of values in that book, it's there. So the second term here is one we look up, or one that will be given to us. What we have to calculate always will be the mole fraction here. And obviously, the more concentrated the solution gets, the lower that mole fraction is going to be, the lower the vapor pressure is going to drop as a result. What the solute is doesn't actually make a difference. That's what makes this a colligative property. It's based only on the concentration, not on the identity of the solute. Now, as we saw in chapter 6, and as we saw with that simulation lab that you did last week, there is a relationship between vapor pressure and temperature. One important thing to note is that we consider the boiling point of a liquid to be when the vapor pressure of that liquid reaches atmospheric pressure. Now, we saw this in chapter 6 with the idea of phase diagrams. If I increase the pressure, the boiling point changed on me. The freezing point changed on me. And this is the reason why. Our definitions tell us when these kinds of changes occur. Now, just looking a little bit ahead to next Monday, we're going to talk about how phase changes are impacted by the presence of a solute. Well, this kind of gives you a little bit of foreshadowing into that. If the presence of a solute drops the vapor pressure, and that vapor pressure needs to reach atmospheric pressure in order to get to boiling, well, we've just increased the gap between vapor pressure and atmospheric pressure. You can make a pretty well-reasoned argument that's going to require more energy to get to the boiling point now than it did before. Now, that first example of Raoult's law applied specifically when we had a solute that was not volatile. That is, that did not evaporate on its own. If we have volatile solutes, that is, ones that also evaporate, so let's say that we are talking about a mixture of liquids, and liquid number 1 and liquid number 2 both have vapor pressures. How do I determine the total vapor pressure of the new solution? Well, it's actually not that difficult. All I have to do is apply that equation for as many volatile particles as there are. So all that these 1s and 2s represent are volatile components of that solution. So let's say, just for example, I have a mixture of ethanol and water. Ethanol is volatile. It evaporates. Water is volatile. It evaporates. Put them together, the solution that they create will also evaporate. How do I know how much it evaporates? How do I know what its vapor pressure is? Well, I look at the two components individually. I look at the mole fraction of the ethanol and compare it to the mole fraction of the water. And I basically just do the Raoult's law calculation once for water and another time for ethanol. And since those are the only two components of the solution, that's all I would need to do. Now, if I had water and ethanol and isopropyl alcohol, all three of them together, all three of them volatile, then yes, I would just keep adding cars onto the end of that train. But the calculation on that, each individual piece would be exactly the same. The mole fraction of the component I'm looking at multiplied by its normal vapor pressure at that temperature. And then I would add on the mole fraction times the vapor pressure for the second component, and the third component, and the fourth component, until I run out of volatile components. So what's important about this kind of equation here is that we really can just make it as long or as short as we want. Let's just say, for the sake of argument, that we're talking about water and sodium chloride. Well, if it's just water and sodium chloride, water is the only volatile component in that solution. There is no volatile component 2. There is no volatile component 3. The vapor pressure is just the mole fraction of water times its normal vapor pressure. It's exactly the equation I showed you first. If there are multiple components, I just add on for however many that there are. Now, this goes beyond the scope of this course, but this relationship is actually one of the ways that we can separate volatile components from each other. It's a process called fractional distillation. But the idea is basically we can use the varying vapor pressures to separate two components of a solution from each other. And that's more or less what goes on in fractional distillation. That's how we can separate two components that have very close to the same boiling points as each other from each other. Now, Raoult's law does give us a little bit of an idealistic kind of view of a solution. So when a solution behaves according to Raoult's law, we say that that solution is behaving ideally. So an ideal solution is one that behaves according to Raoult's law. What we have to understand is that intermolecular forces don't always behave exactly the way that we would expect them to. And so that's where these deviations come in. And we can expect deviations when the environment does not behave exactly the way that we anticipate. So for example, chloroform and ethanol. I've got two polar molecules there. If it behaved ideally, what we would expect is that their individual vapor pressures and the total vapor pressure would fall on these dashed lines. But as we can see in this graph, they don't fall on the dashed lines. In fact, in each case, they're above the dashed lines. Now, why is this the case? Well, as it turns out, chloroform and ethanol don't actually attract each other nearly as much as we would anticipate. Their intermolecular attractions are actually weaker than what we would think they are. And so as a result, we have weaker intermolecular forces than anticipated. We're going to get higher vapor pressures than anticipated as well. That's called a positive deviation from Raoult's law. Now, negative deviations can occur also. Those negative deviations would be when we have circumstances where they actually attract each other better. And so everything dips below the anticipated lines. Let's take a look at an example. Most of the world's supply of maple syrup is produced in Quebec, Canada. The concentration of the sugar in the sap reaches at least 66% by mass. What is the vapor pressure in atmospheres of a 66% aqueous solution of sucrose at 100 degrees Celsius? Assume that the solution obeys Raoult's law. Okay. So what we need to pull out of this is that we have a 66% aqueous solution. So 66 grams of sucrose for every 100 grams of solution. So a little bit of quick math there. We have 66 grams of sucrose, and we have 34 grams of water in that solution. Now, our equation, Raoult's law, is we need the mole fraction of water multiplied by the normal vapor pressure of water at, in this case, 100 degrees Celsius. So, to figure out the mole fraction of the water, I'm going to have to do some calculating. Calculating I'm doing here is I need to calculate the number of moles of sucrose and the number of moles of water, add them together to figure out the mole fraction. Molar mass of sucrose, 342.30. So 66 divided by 342.30 is 0.19 moles, 18.02 grams of water in a mole. 34 divided by 18.02 is 1.9 moles. So the mole fraction of water would be 1.9 moles of water divided by the total of 1.9 plus 0.19 moles. Vapor pressure of water at 100 degrees Celsius is kind of a trick question. You have to remember what the relationship is. 100 degrees Celsius is what we would consider the normal boiling point of water. Well, at the normal boiling point, at any boiling point, vapor pressure and atmospheric pressure are the same. So we would anticipate the vapor pressure of water under normal conditions would be 1 atmosphere here. So 1.9 divided by 1.9 plus 0.19 in the denominator gives us 0.91. Notice moles cancel out of this. Mole fraction is a unitless concentration. 0.91 multiplied by 1 atmosphere would give us a pressure of 0.91 atmospheres. So the vapor pressure of this maple syrup is 0.91 atmospheres. It hasn't started boiling yet. Remember, to boil, it would have to be at 1 atmosphere. So at 100 degrees Celsius, this maple syrup is not yet boiling. Again, looking a little bit ahead to next Monday. Next Monday, we're going to talk about how solutions, how the presence of those extra molecules impacts the temperature and pressure conditions, impacts the ability of some solution to freeze or boil. Well, we already can see some of the effects here. That solution, which would have boiled if it was pure water, isn't boiling yet as a solution. So what does that mean? We're going to have to raise the temperature to get it to boil.